Hello, everyone. Thanks for coming to the Temporal Graph Reading Group today. Today we have a great speaker here, Kiarash, who will be presenting their paper, Chartalist, labeled graph datasets for UTXO and account-based blockchains. This is a joint work with his supervisor and other collaborators. So. And our speaker today, Kiarash Shamsi, is a PhD student in computer science at the University of Manitoba in Canada, and he have obtained his master's and bachelor's degree in computer software engineering from the University of Science and Cultural and University of Science and Technology in Iran. Kiarash's research interests revolve around machine learning, deep learning, data analysis, and blockchain technology, focusing on their practical applications. Kiarash is contributing to the advancement of these areas through research and publication, with his work being featured in conferences and journals such as NeurIPS, ICBC, and IEEE Access. Machine learning on blockchain graphs an emerging field with many applications, such as ransomware, payment tracking, price manipulation analysis, and money laundering detection. We also have Junet here, who is Kiarash's supervisor. Junet Gurkhan Akora is an assistant professor of computer science and statistics at the University of Manitoba in Canada. He received his PhD from the University of Insobria, Italy. His research interests include data science on complex networks and large-scale graph analysis, with applications in social, biological, Internet of Things, and blockchain networks. Akora has been awarded a Fulbright scholarship and has published his research in leading conferences and journals, including IEEE Transaction, KDD, NeurIPS, VLDB, ICDM, SDM, IJCAI, and ICDE. I will hand the mic to you, Kiarash, to get started.
Thank you so much, Andy, for this introduction, and let me get started. So thank you for having us here, and today I will present our Chartalist project, which our paper has been published as a dataset and benchmark tracking NeurIPS 2022. And basically, this project was a collaboration from University of Manitoba, University of Texas, Dallas, and TU Berlin from Germany. So basically, the title of paper is Chartalist label graph datasets for UTXO, such as Bitcoin, and also account-based blockchains such as Ethereum. And in this presentation, first, I'm going to present and talk a little bit about the introduction and what's our purposes here, and why we need like this kind of ecosystem blockchain research field area, and then our contribution, our contribution, and then I will present talk about the UTXO blockchain data models and also our tasks from the Chartalist on UTXO blockchains, and then account-based blockchain, and also the tasks on account-based blockchain, and then we will talk about temporal data analysis on blockchain. That is like the purpose of this meeting. So as a brief introduction, so today's machine learning is expanding very fast on blockchain graphs and blockchain research area. And we have lots of many applications here in this domain, like ransomware, payment tracking, crypto assets, price manipulation, analysis, money laundering. And all of these are not just about cybersecurity. We have lots of other different also tasks here in machine learning on blockchain graphs, such as price prediction and also address clustering and linkage. And the thing is that here in this area, it's a little bit hard for ML community to start like projects and start analyzing this blockchain data, because Starting an ML project on this area of research, blockchain and blockchain graphs, requires a domain expertise, and you should have lots of information about how these networks are working and different data types here, different graph types here, and how to work with them, how to extract data from them, and it's a little bit hard and challenging here. And the second thing here is you need a huge computational resource to get like the data that you need for starting with your pipeline at the first stage. And this is a kind of a very significant barrier hinder for advancement in this field. And people like to not gonna start any project in this area because of these challenges. So prefer to start projects on other different graph networks rather than blockchain. Our current stance in blockchain is we are growing fast here every year. So right now we are more than 600,000 transactions and blocks here in blockchain network. And the thing is that for starting a project here in this area, you need a significant effort, like to extract all the underlying graphs and the running blockchain clients. And maybe you need to pay for commercial APIs to download these transactions. So it's not a cheap process to get like your data. And also you need a very huge resources, considerable resources to construct these blockchain graphs as well. Because these are very huge graphs, like a transaction graph of the blockchain, like Bitcoin network. It's not like a tiny one. So you need a considerable resource to extract the features of that, to extract even the graph of that. It's very time-consuming and a costly process. And also in this area of research, you don't have any kind of label data, any ground truth, because it's like transaction graph. So you have like this transaction graph, and there's no like lack of label data for starting a supervised learning task. And the thing is that since we have like two different model of graphs here, the UTXO model like Bitcoin and account-based blockchain like Ethereum, so it's a little bit hard and tricky to start like a pipeline that can work with both of them. And like the extracting graph part of these two networks are completely different with each other. And it's hard for like people that don't have like blockchain background to start any tasks in machine learning in this domain. So this is like a great motivation for us to start our dataset and benchmark project called Chartalist. And Chartalist is the first ML-ready dataset ecosystem for unspent transaction outputs, UTXO-based networks such as Bitcoin, and also account-based blockchains such as Ethereum. So in Chartalist, we have three main contributions as components. So first, in Chartalist, we create a holistic view of blockchains and formulations of all graph machine learning tasks that are available in this domain. So you can access all of the things that you need to know about how you can process the blockchain data and create graph networks and try to start your ML works and ML tasks on that. So it's a very good starting point for any people that wants to start working with this area and the blockchain data, basically. And we have a comprehensive ecosystems. We have tools, open source tools, and support blockchain data analytics tools that you can access them in open source like our GitHub, and it's very easy for you to create graphs and everything that you need for that. And also at the end, we have a set of boards and leaderboards to support like your performance comparison and benchmarking tools. It's a very good starting point for everyone that wants to start like a kind of research on this area. Blockchain data analysis. Before going to tasks that we can perform on this data set, so we need a little bit more to know about like data models and graph types here in blockchain. So before going directly to tasks, I need to little bit talk more about like what's going on behind like under the hood. On different blockchain, the UTXO and the account base, and then we will go to the tasks and what can you do with these graphs. So the first model here is transaction output based blockchain. So this is UTXO based models and lots of different transaction networks, a lot of different coins basically are using these type of networks. So Bitcoin, Cardano, these are two most famous ones. So basically in UTXO transaction networks, we have two different nodes here in graph. So we have transactions and addresses. So when we are creating like the graph out of UTXO data, so we're dealing with two different type of nodes here, like the circles are addresses and like the other one is transactions. So we have two different type of networks. And basically in these networks, like we can have multiple inputs and we can have multiple outputs. But the thing is that like more than half of the transactions here in this Bitcoin network, we have like just one input and two outputs. And we have a reason for that. It's because the senders should send them money to transaction and it's changed to itself and like the amount to the other addresses. So I will talk about this in the next slide. But basically, the things that you need to know here is that so in this UTXO graph, transactions are not that much easy like any other transaction network, like financial network, banking network. These have one destination and one target. But here is not like this. Here we are dealing with a little bit more complicated networks. So basically, this is a kind of example for sending money from a source like to two different targets. So consider that this user wants to send 0.8 Bitcoin to address A and 2 Bitcoin to address B. And the thing is that, so here in this graph, we have the traditional transaction graph that can be very straightforward. But the thing is in UTXO network is not like that. So this user should send like this 3 Bitcoin as a UTXO block to transaction. And in this transaction, these amounts should went to like the A and B addresses. It's like a little bit more complicated. The thing is that here in the blockchain network, in UTXO network, Bitcoin, all of the transactions should somehow show the proof of funds. It's something like that. So, for example, consider that in this transaction network, if this B wants to send 2 Bitcoin to C and D, it should say that something like that. So I use the 2 Bitcoin I received from block 1, transaction 1, and to pay 1.5 Bitcoin to C and 0.3 to Bitcoin D. So everything here needs to have like a kind of connection to the last block. So we need to trace this, and it's a kind of show proof of funds here. A little bit more about the
just
Bitcoin.
A quick question, Kiarash. So if I understand correctly, what you are saying is that if we track all the edge weights plus the node weights, the node weight is kind of the leftover transaction amounts, like everything in the graph should have a constant total, right? Because the number of Bitcoin should be fixed, if that makes sense.
It's not like that. So the number of coins is not fixed because like in mining process, I will talk about this in future in the next slide. But yeah, we are adding like in the Bitcoin network, we are adding like more and more like coins in each block as a reward to miners. So this is not a constant amount, but somehow there is a kind of tracking in that. So you cannot spend money without any proof of funds. So you should receive this fund and then spend this fund like in the way of like chains here.
But the total is the total should be strictly increasing. If you look at the total across the entire graph, because you can only mine new Bitcoins, you cannot lose previous Bitcoins, right?
Yes, exactly. But the thing is that, so here we have, the overall, in theory, you're true, but the thing is that, so we have lots of different dead coins here. So we have addresses that they have like UTXOs, but they are not doing any transactions. So these amounts are somehow, they may lost their addresses, they may lost the access to their addresses. The network is a little bit complicated. It's not that much straightforward. That's why I'm just explaining all of these things, and then I switch like to tasks to show that this is not like a very simple task. It's a little bit complicated here. So we need like a kind of tools to facilitate this task for us.
That makes sense.
So,
thanks,
you're welcome. And a little bit more about like blockchain, Bitcoin, specifically UTXO based blockchains. So we have like a Genesis block. This is the first block that created by like the creator of block, the Bitcoin blockchain. And then we have like in each block, we have a Coinbase, which is like, as you said, this is like the sum of block rewards and transaction fees that goes to like miner addresses. So if you look at here, so we have this Coinbase transaction here, and this goes like to this address, and this address definitely should be the address of the miner of this block. So, and also we have like some other transaction that's going on in the chain. So we have like this, and in the next transaction, we have these transactions that somehow connected to the last transaction or from the last block. And the thing is that I really want you to consider in all of these data that this time, we have like this time stamp everywhere in blockchain data financial network. And I will talk about this in my second part of presentation about temporal aspect of this like blockchain and all of blockchain networks and how can we process them here. A little bit more because I want to switch to the task. And the thing is that here in Bitcoin network, creating addresses are super easy. It's just creating like address, like a public and private key, and like a person, owner can have like infinite number of addresses. So you can create as much as address that you want. And the thing is that this process is very cheap. So you should not pay anything about that. And also in other side, sending money to someone, you need just the address of that. So this address, and this is a very cheap process. So it can cause a lot of difficulties in processing the data, because like you can have many different addresses, and like finding these addresses, processing these addresses, especially in cybersecurity area of research, is very hard. This can have some pros and cons in blockchain, in Bitcoin network, but this is the way that it works. And basically in terms of the meaning of the output and input of the transaction, so in a transaction, so we have like multiple output addresses, and these addresses can be related to completely unrelated people, or it can be somehow from same owners. So there is no rule on that. Basically here, the C and D can be completely unrelated people, or they can be like belong to one person. So there is no rule here. But in terms of inputs, so since like inputs of a transactions, all these addresses should sign this transaction, there is a good chance and good probability that these people knows each other. And this is like a basic, very basic pattern here in blockchain network. I will talk about this in the future, so in the next slide. But this is one of the facts that we can extract like from a blockchain, Bitcoin networks. That we don't know anything about the outputs, but we can somehow make sure that in the inputs, there is a correlation between these addresses that are participating in a transaction. And in terms of rules, we have three main graph rules in blockchain graphs. In terms of blockchain, right now I'm speaking about the UTXO. So if I say like blockchain, my purpose is like UTXO blockchains, not account-based. So that's in terms of more terminology. So in terms of mapping rules here in UTXO network, the first important rule is that so there is no mapping between input of a transaction and output of a transaction. So like consider this transaction block as a kind of lake. So you have some incoming rivers to that, and you have some outgoing rivers to that. So it's a kind of coin mix here. So you cannot say that, okay, these one Bitcoins come from here, go to like these addresses. So there is no tracking here. So you can't know any information about that. So we have some inputs, we have some outputs, and there is no mapping between them. So this is the first rule that you need to consider if you want to work like with these graphs and understand like our tasks here in UTXO network. And the second important graph rule here in UTXO is our source rule. So consider that in a transaction in like a block, an address can gain multiple transactions and multiple points from different transactions. Like here, consider the B, and gets coins, UTXO blocks from this transaction and this transaction. So it has like two bunch of coins from two different transactions. And the B can send all of these things together to one transaction, like TX1, or it can separate these things in two different transactions, like TX1 and TX2. So both of them are problems. So we can have both of them, or we can have just one of them. And again, for more clarification, circles are addresses, and these shapes are rectangles are transactions. And the second and the most important rule here is that, so when you have like a coin, and this coin that we call it UTXO unit came from a transaction, you shouldn't spend all of these UTXO together for the next transaction. So consider that you get 3 Bitcoin from your last transaction, and you want like to send 2 Bitcoin to address D. So you need to input all these 3 Bitcoin to transaction 2. So you cannot separate like this. You cannot like break these 3 Bitcoin to 2 and 1, like, and send just 2 to the transaction. You should send all these 3 Bitcoin to these transactions, and in these transactions, so 2 of this Bitcoin can go to B, and then you can have like your own address again here as E, and get the change of that, like in this transaction. So this is a very, this is one of the most important rules here in blockchain that can define lots of different tasks in machine learning domain here. So consider these 2 scenarios. So consider that we have like this C, and C sold all its coins. So it can send like a part of its coin to D and a part of that to E, or can like send a part of that to D and the rest of that goes as a change to his own address. It can be the same address as C, or it can be like another new address. So the thing is that basically in Bitcoin blockchain network, reusing an address is rare. So because creating address is cheap, so nobody uses like the same address 2 times. Many people use that, so it's not something that never happened, but it's not that much popular. So people prefer to make new addresses. So knowing all of these things about the UTXO, these are the basics information about how this graph shape and what's going on here under the hood of UTXO network, we can switch to the task that we define here. So the first task of Chartalist dataset networks is anomalous transaction pattern detection. So basically in this task that we are somehow defined on Bitcoin transaction networks on these UTXO graphs, we are looking to identify transaction patterns that are used in somehow adversarial and illicit cases. So we have some, we know that we have some bad patterns, and we want to detect these kind of patterns on this blockchain network. And this is a very, very hot topic of research here in blockchain community. For this purpose, we created a blockchain Bitcoin network. This is about 100 gigabytes of data, and we have like more than 700,000 blocks of Bitcoin UTXO network. And we can create like a graph of that with Chartalist and start processing that. So basically, to give you a better idea how these tasks work, this is one of our examples from our research paper from our research group that we currently found this pattern on Bitcoin network. So basically for this task, our goal is detecting the patterns that are somehow anomalous. And this is one of the patterns. So let me describe this pattern so it can be, so I think after that you can better understand what's this task exactly. So here is a ransom payment pattern. So consider that we have a ransomed entity. It can be a municipality, it can be a hospital, it can be even a person. And consider that the hackers ask this person to send some Bitcoins as a ransom to this address to like kind of ransom the purposes. So basically, this is one of the most important and most popular behaviors that people do after they get ransomed. So this is basically that this is the address of the ransomed entity. So consider A1 as the ransomed entity, and when hackers ask this A1 to send coins to us, so the first thing that A1 will do is going to ask exchange to buy some Bitcoin. And this is the act of the like exchange. The exchange gather all these coins, these UTXOs, and send a huge amount of UTXOs to the address of this person. And this makes sense because this person needs some Bitcoins at the first time to send it to the hackers. So this is the initial point of this pattern. So we have something like that. So we have a huge number of inputs here in this side. All of them get to a transaction and come here to this address one. And basically consider that here we have 0.5 Bitcoins for the ransom. We need this amount to send to hackers for the ransom purpose. And then based on our research, it takes like around 1 hour. It takes more than 1 hour, or around 1 hour. From transaction 1 to transaction 2 is basically different. It can be from 1 hour to 24 hours, 1 day basically. I think this is not 1 hour, so it's a mistake from me. It's 1 day. So from transaction 1 to transaction 2, and in this transaction 2, these ransom entities send like this amount to the dark addresses, and if there is any change to his own address. So this is one of the patterns that if you apply this to different networks, you can find many different ransomware addresses. And we did that before, and we could find that this is actually a working pattern. So with this single pattern, you can detect some important ransom addresses. So and basically in this task, we are trying to find more and more of these patterns here. So it's a pattern mining task. And this is one of our baselines. So anybody wants to start like working on this area, then start looking at a paper here and how we detect this pattern here and start to going and work and try to find other different patterns. So this is from our research group. Yes, and any question here?
And then after the amount is put to address 0, the dark node that you put here, it still needs to spend it, right? It can't just hold the Bitcoin. If you don't spend Bitcoin, it doesn't have value, right? So it still need to give it to somebody else in order to actually make real world money out of it, right? So
exactly. So basically, based on your question, I'm gonna define our next task here. So
okay,
it's a very good question. So after that, we have our next task. Our next task here is address clustering. Exactly. So we have like this A0, and like the hacker is smart enough to don't hold this amount of money in one single address. So it's break this amount to different addresses and spend it send this huge amount of money to lots of different addresses. So this is particularly very important task. So this is one of the most important tasks here in blockchain data analysis. So it's governments are interested in, financial institutes are interested in this task. So the thing is that you want to cluster and find all co-ownership addresses in one single cluster. So you need to know which addresses belongs to one person. And this has lots of different use cases. One of them is, as you said, is for detecting finding darknet or dark community. Is for tax purposes. So because people break this amount to different addresses, should not be tracking and pay tax for that. It's another thing. For financial institutes, it can be useful to find the actual amount of the wealth that people have and these kind of things. So this is particularly very important task here in our data set. So again, you can use our Bitcoin UTXO network here with our 100 gigabyte of data, and we have the tools here for that. And the goal here in this task is a little bit different from that. So it's it's the baseline for the next step of the previous task, as you said, Andy. So here we want to invent a new clustering heuristics for UTXO-based blockchain. So we have this graph, and we want to somehow cluster these nodes together. So for better understanding, this is 2 basic heuristics that we are using in some of our papers. And we have lots of different other heuristics that you can go for that. But these are the 2 most easiest. The first is co-spending address heuristic. So in this heuristic, you say that, okay, all input addresses of a transaction belongs to the same users based on the fact that previously I mentioned here. So because all of them should sign a transaction. So we can probably say that they may know each other too, because they are signing a transaction together. It can be belong to a person, or these people somehow know each other in a way. So this is the baseline of this heuristic, and we extend this heuristic again and say that, okay, if one of addresses from this transaction participate in another transaction, we can consider all the inputs together to be for a person, same owner. And it makes sense because like we have like these trees are for E, C, E, and D and E are for same person, and A, B, C are for same person, because C is in both sides, so we can say that all of them are the same, like page for one person. So this is basically our second task here in this area. And our
sorry for interrupt. So just wondering, because data set is pretty big, so is there any labels saying these addresses are the same person's addresses? Like the heuristic are used to finding the patterns to detect or do the clustering, but do we have any branches labels? I mean,
I will talk about that in my next slide.
Oh, sorry. Yeah.
Yeah, we have like labeled data sets here. And these labeled data sets is one of, again, another research paper of ours. It's Bitcoin Heist, and you can look at that. It's particularly gathering information from the other three different research paper, and then we create all of these methods and try to label the data. And we have like a labeled data here for using these purposes. And just I only recommend you to read that paper, Bitcoin Heist, but I will talk a little bit about your question here again. So our next task, and somehow related to the previous one, is basically ransomware address and transaction classification. So in the previous one, we have clustering, and here we have classification. And for these tasks, we have like this data, and also we have another labeled data points. So in these labeled data points, we have we created a label for ransomware addresses and void addresses, basically from one of our research papers. And you can use these data sets to create two different tasks, as well as the previous one, for making sure that the clustering is working. So in these data sets, we have like extracted 10 features from Bitcoin transaction networks. And the thing is that here, extracting features from Bitcoin and UTXO networks is an open area of research here in blockchain. So because like you have like this graph, and you need to extract interesting feature out of that, and it's another task here. It's basically a research area itself. But here we created like extracted 10 different features, and again you can read that paper about this. And basically, based on these labeled datasets, we can perform two different tasks. So we have like a classification task. So it's a supervised learning task traditionally. So we have these features, we have labels, void addresses, and also ransomware addresses. So you can consider it as a binary classification. And we want to predict addresses like that or ransom or not in this data based on the current labels. And the second and the most interesting part for me particularly is temporal prediction. So we have like these addresses, we have the data until like time t, and we want to train a model on this and like predict the labels for the time 3+1 for the future. So this one is actually like more industrial ones, more like important ones, because it can have many use cases like in real world. It's not just a research project here, because you can predict like the ransom addresses and real time somehow in the future maybe. By future, I mean like the current time here. So you can have like a kind of real time pipeline here for predicting the ransom addresses, not from a static graphs here. Basically, these three tasks were on like our UTXO models, and the next model is the account-based blockchain model. So the good news is here we have like simpler graphs and data types, so it's easier to work with them and like understanding them or a little bit more straightforward. So here in Ether transaction, like you have basically based on all of the transactions that you have in a transaction network, you have a source and you have a target, and this transaction can be a straight line between them, and you can find who is like sending this money to who, and this can be a mapping. So in UTXO we don't have this mapping, but here in this transaction network you can say that okay, address 1 is sending money to address 2. This is a very clear thing here. So each transaction has one input and one output, and the thing is that here address spends coins from a balance. So we have change, we can keep change, but in UTXO we cannot keep change in addresses. So addresses have different UTXO, that if you want to find like the balance of address, you should like go from the first block to the end of the block and try to extract all of the UTXOs for this address. UTXO block on a span block, but here you have like the chain, you keep the change. And also the thing is that here a later transaction needs to wait for the earlier transaction to be mined. So we have like a time-based transaction. So we know that the transaction A is before the transaction like B, and that's a good thing for data mining, for pattern mining in the next slides, and I will talk about it. In Ethereum transaction network, so we have 3 different type of transactions. So we have some transactions based on ordinary address to a contract address. So we have like smart contract transactions. We have like very ordinary transactions from address 1 to address 2 for like sending currencies, Ethereum here in this case. And also in this network, we have token networks. These are tokens that are based on a smart contracts. And these are a very popular area of research here in Ethereum. Lots of different projects on that, and you can do lots of different interesting things here in this token networks particularly. So basically this is a transaction graph, a complete transaction graph of all possible different transactions. And this is like has an order here. So we have a story behind that. So consider that the first transaction start, B wants to buy 3 coins, 3 token coins from this smart contract, and each coin is, the price is 0.15, 0.15. And so B sends 0.3 Ethereum to this smart contract and buy 2 coins. And after that, A wants to buy these 2 tokens from B, but the thing is that the price of this token dropped to 0.1. So A should spend 0.2 Ether to B to get like these 2 tokens. And after A send this 0.2 Ether to B, B send these 2 tokens to A. So all kind of different transactions are here in this graph. So we have like a smart contract transactions. We have ordinary currency transfer here from A to B, and we have like the transfer of token from this B to A. And this is like a complete transaction graph here on Ethereum network. The first task, and one of the most important tasks here in this area of research, is stablecoin analysis. It's a kind of very hot topic after Terra Luna crashed, if you heard about that. And it lost lots of money for the investors. So the thing is that here we have like lots of different stablecoins here on ERC20 network, Ethereum network. Basically, in our work, in our dataset, we have 6 token networks of them. And the task here is to detect the time when this stablecoin crashed something, and to also look for any like anomalies and any illicit activities here in this transaction network to predict any crash or misbehavior in the future. So this is basically one of our tasks here, and our research team currently have a paper on that. So we have like a paper on that, especially for the stablecoin market. And the goal here is to gain insight into like market behavior and activity So at the time of the crash of this network. So this can be also a very good area of research because it has lots of use cases here right now in the market. So, and the next and the most important tasks here in quant-based networks is that we have the token networks of 1,701 different token assets here. And we can, and these are all graph-based networks. So we have different token network graphs for different tokens, and we can perform lots of different tasks here. And I have the current project on this multi-layer network analysis. So we can do address classification here. We can do address clustering, anomaly detection, graph classification, and all other different tasks here. So this is a very vast area of research. You can do different kind of tasks here. But if I want to like make it more clear, so here we have like this network, and people on this network can invest on different like assets. So one address can have multiple tokens and can participate on multiple token networks. So in these tasks, our goal is predicting events and some phenomena that emerge like through these networks, through like these networks between these tokens. One of them can be like the trend of network, the price of network, like the behavior of the network, the crash of the network, all of these features of the network we can predict based on these token networks. And the data in here, the data model here is a directed weighted multi-graph. And the network here is very sparse. So this is a feature of this network because these tokens, like lots of these tokens are not that much popular. So we have a very sparse network, and this is a challenge. So like working with these graphs and like start doing some ML tasks on this graph is not like a kind of easy task here because the graphs are not like a regular task like social media or this kind of network. This is like a very special network because of the financial networks, and it's super sparse. And we have lots of different components because we have lots of different communities, and these communities are just trading with each other. So we have like different daily components, different disconnected components. And this is like through the nature of these networks, because token networks have their own investors. So each network particularly. And the thing is that basically this token network is very good for data mining in temporal or multi-layer network. So because we have daily timestamps here, and we have like daily graphs, we have like everything that you need for temporal data analysis on these networks. So, and also for this network, we have one more thing. We have blockchain events, and this is from like the outward. This is like, for example, China bans cryptocurrencies, token price event, these kind of things. We have like external ground truth datasets that has all these events, and you can use this as a kind of label if you need for processing and detecting these anomalies and event and phenomena here in this network. And the last task here is price prediction. It can be interesting task somehow, but it's a little bit hard to perform like a good prediction performance here. So we want to use all of this observable blockchain activity to predict like the assets and the price of the asset and coin price. So basically we have these graphs, we have all the features, we have this ground truth event. We want to use everything that we have here to predict the price of this token in the future. It can be somewhat interesting. So these are all the tasks that you can perform on our datasets, and you have the tools, you have the baselines here. And in next slide, I'm going to talk a little bit more about the temporal aspect of this data and how we can perform temporal data analysis on blockchain. So yes, Andy.
Just a quick question before you move on to the next slide. For the price analytics, have you tried some just time series models?
Yes, we have again another paper here. So if you go like to our data sets, we have again a good paper here for like predicting the price of tokens. And it's still a kind of ongoing area of research. So we have different papers from even like financial people. It's not just like a CS problem here. So this is a kind of more vast area of research. So you have computer science people, you have business people here. There are lots of different factors here. It's not just the network and like graph and machine learning tasks. So you have lots of other different things that can have effect on predicting this task. Because of that, I said it's a little bit more complicated task here.
Do you know how well does like just using time series work, like in a rough sense? Does it work well, or do you think the graph structure will contribute a lot to the
I think time series can perform like based on our research, but I'm not sure if we combine these things together and like create maybe a hybrid way to doing that, or also a graph one can improve it or not. So it can be a good like search in the next group.
Because this also sounds like something that's on the graph level prediction for temporal graph, right? So you have a one number per graph, and then you track everything until time t. You want to predict the price for t+1, but it's a graph level task because you want to look at everything happening in the graph to predict the task.
Exactly. Yeah. It can be a graph, it can be time series, but I said this is not just a computer science task. I need to consider that, because you may have lots of different patterns here in this network, but after like just one happened, like for example, China banned like the cryptocurrencies, so everything's like going somehow. We have like shifts here, distribution
you
shifts
have like
and
outside. You have like external events that's not just the network structure that will affect the performance.
Exactly. You need to analyze like different things here. It's not just based on like the graph and these kind of things. You need to like track other things to like have a good price prediction here, because it's not just basically based on the network. So for example, ransomware, there are some patterns here in this network, clustering, these kind of tasks. But here it's a little bit more challenging. You need to consider lots of different things. So because of that, I said it's not just a computer science basically task here. So you need to, there are more here.
Thanks.
So like starting with the next part, and this is like the part that we are more interested in this talk. So temporal data analysis on blockchain. And the thing is that here in blockchain, we have everything timestamped. So we have transactions, all transactions, they have time. And also we have transaction calls, asset transfer, everything here with time tags. So we want to use these time tags as a temporal kind of feature. So we will mine data from the content graph, we will create this content graph, and we almost always in this blockchain, we divide a blockchain network into maybe daily windows or like some windows, because this network is very huge. So you cannot process all of this network together. So you should break these networks, and you have lots of interesting temporal features. Like you have one behavior, one pattern, and you may have another different pattern like in the next day or next month, and you need to somehow have some kind of these temporal features, and this is a very interesting things to do. And the thing is that, so here I just want to make an example to make like more sense here, just to explain what's going on here. So this is an example of temporal data structure of UTXO graph. So we have 3 days, and we have different transactions and different graphs here, and it may have some like connections here, or it may not. For example, here we have A1 here and again A1 here, so we have a kind of connection between day T and day T2. So we want to mine these kind of patterns here. So this is an example of how data looks like here in this temporal data structure on blockchain. And in this temporal data analysis on blockchain, we can extract 3 types of features and 3 types of tasks. So we have node features, because we have like different graphs. We can work on node features, we can work on edge features, and subgraph and graph are the graph level features that we can extract and start like working on this based on different temporal graphs here. And also, this is another example of how daily features of an address look like. So we have daily features and we want to extract some temporal sequence feature out of that. So this is one example for that. So we define two features here, degree and one hop neighbors. So one hop neighbor is the number of neighbors that are in one hop far away from the base address. So consider we have these A1 and the one hop address is this A2 and A5 because we have one transaction between them, and we consider this as well because this is inputs are important too. So and we create something like this. We have a sequence of degree and one hop, and we have this for like each day. And this is like a very basic example. I'm just explaining this to make more sense how you can use our dataset for temporal data analysis. So you can like define lots of different features, create more complex sequence, and use different time windows approach and whatever you can like imagine in the temporal area of results. And then after creating like this sequence, you need to somehow perform a temporal prediction task on that. So we have supervised learning. So because we have some external labels, and also we can perform like unsupervised learning on that. So in all kind of temporal data mining tasks on blockchain area and blockchain network, we have something like that. So we have like from T-4 to T. This is our training. And also we have like a horizon, and after that we have like a prediction. So we have like T1 and T2, and we need to predict these things. So basically, I think this is true for all kinds of temporal tasks, but here in blockchain, we go for based on the things, based on the example that I show you. So we have like something like this. So we have graphs for these things, and we want to predict something in T1 and T2. There are lots of different approaches here. One of them is like moving sliding window. So we have like sliding window starting from T-3, going through the time and starting gathering sequences and trying to process the sequences of time and temporal features. So we are predict time-based. And again, I think this is true for all kinds of temporal features, but here in blockchain, these temporal features, you can perform very interesting tasks to predict different features in blockchain. And as the last slide in this temporal feature, so again, we have like this T window, and we have like the features label for T-3, -2, and -1. We have one validation feature, and we want to predict some label, maybe T+1. This can be the way that we perform temporal data analysis on blockchain networks and blockchain graphs. So Chartalist has all datasets and tools that you may need to start working on blockchain temporal data analysis and all kinds of different tasks that I explained before. So you have everything that you need to start working on this blockchain area. The thing is that people somehow afraid to start working on blockchain networks because they don't know where to start, when to start, how to start. But here you have like your baseline, here you have your data sets, here you have your open source tools to extract the graphs. You just need to go through that, start a little bit more reading and try to define your method and go through our leader, make a better method. To wrap up all of wrap up this slide, Chartalist contains clean and labeled data for all UTXO based blockchain like Bitcoin and also the Ethereum count based data. So we have open source data loaders, we have graph extractors for easy analysis. We have large scale dynamic multi-layer networks where all these nodes and edges weights evolve. You have everything that you need to create like the multi-graph weighted graph out of this network. We have ground truth information if you want to do any supervised tasks here. And also we designed a leaderboard for tasks which has been studied previously, for example, such as price prediction, that we have a paper on that, clustering classification, ransomware classification, and we will like add new baselines to our leaderboard if we can find like new methods that can perform better on these kind of tasks, both in UTXO network and also the account-based one, Ethereum-based one. So, and also the thing is that we have lots of other tasks that can be performed. So these tasks are not limited just to these 6 different tasks. So maybe we can define even new tasks here in this area. So we have this graph. You can also define your own tasks here. We are more than glad to add these tasks also to our website. So if you can find like new tasks on this networks, on this blockchain area that is interesting for industry or for academia, we are more welcome to send like your new tasks and description to our website, and we can add these tasks also to our website and put your baseline as the first init leaderboard to that task as well. And also our datasets are available at Snap Stanford repository, so you can access that as well. So our stablecoin network are available there, so you can use that. And also our websites, chartalist.org, you can use that. Everything is there. So whatever you need is there, the tools, the baselines, the leaderboards. And also you can use our GitHub repo to use our tools, graph extractors and whatever you need to extract the graphs and use the data. And also a paper is available for you to read if you need more information on how to use this and what's going on like in different tasks. And it is available on NeurIPS 2022. So thank you everyone for having me here. And that was like my presentation for Chartalist. And I hope to see you soon in blockchain data analysis conferences and also read your papers. And I hope I could somehow encourage you and motivate you to join us in this research field and try to make like different new methods and interesting ones in graph and neural networks, graph, machine learning, also data analysis, temporal data analysis on blockchain data sets and blockchain. Thank you. If you have any question, I'm here to ask. I'm here to answer.
Yeah, thanks for the great presentation, Kiarash. That was very nice introduction to all the different tasks and the background. So definitely will be very helpful. And also as a side note for everyone, if you're interested in contacting Kiarash, he's also on the TGL Slack. So so Slack can be a way to do collaborations as well. Yeah, unfortunately, we don't have time for too many questions today, but feel free to forward any question on Slack, or you can send the question to me. I can forward to Kiarash as well. Yeah, I think we are at the end of the hour here. So thanking everyone, and thanks for the great presentation again, Kiarash.
Thank you so much.
Thank you.
Thank you. Thanks everyone.
Thank you.
Thank you.
Bye.
Thank you.
Thank you. Bye.